Hey, my name's John Broadwell. I'm an independent consultant at Broadwell Consulting Incorporated and the creator of the Serial Wombat open source project. Today we're going to look at a prototype early revision of a future update that's coming to the Serial Wombat 18AB chip, which will allow us to drive a VGA display in 7 colors plus black at using only 5 resistors and a hacked up video cable. And what this is capable of doing is using 5 resistors and 5 Serial Wombat pins. This driver is capable of driving a VGA display at 160 by 120 pixels. And it's capable of doing color, but it's limited that each horizontal line has to be entirely one color. Essentially, at the beginning of the line, we switch colors. There's 7 colors available, which is combinations of red, green, and blue, which allow you to also create magenta, cyan, yellow, and white. So it's a pretty fun driver, and unlike some of the other Arduino stuff out there, it doesn't preempt you from doing other stuff with the Serial Wombat chip. It does eat up a significant amount of the Serial Wombat chip's processing capability, but you can still do PWM outputs or servos or whatever. One thing that'll be different about this chip mode than most is because of the high performance requirements, I'm actually generating interrupts about 30,000 times per second. The pins used for this mode will be fixed. They will not be configurable. So there'll be a specific pin you have to use for vertical sync, a specific pin for horizontal sync, a specific pin for R, G, and B. Let's watch this go. I'm going to do a refresh where we blank the screen and write. And so pretty fast, we're going over the serial bus or over the I2C bus. This particular driver does not use a frame buffer. On the host side, it does all of the writes directly in. And you can see right now, I'm still in development. I've got a little bit more flicker. I've got some interrupts that are happening at times I don't like. I'm going to work to try to work that out. Sometimes you fire up the driver and it's real stable. Other times I have these timing variations. So see, I just restarted it now and I'm not seeing that particular flicker. And we can see here down in the bottom, I've got some code that's just reading the temperature sensor on the Serial Wombat 18AB chip and doing a constant update there. Some of this stuff will get a little bit faster. I am working, when I'm running this particular project, I'm running it on a PC, and I've created some Microsoft Visual C++ projects that provide a lot of the same interfaces as the Arduino base. They're actually based on the same code base. I may fork the Arduino base and the Adafruit GFX and all that to make these changes available to everybody. But this lets me do a lot of my debugging and such on the PC, running the code on the PC as if it is the Arduino that's driving the chip. So, and all the stuff is highly compatible. So this particular effort that I'm doing is based on 5 different projects. Wombat CPP is a pointer to the same code that you get when you download the Arduino library from Arduino, exact same .h and .cpp files. The Serial Wombat 18AB VGA project is an additional project that inherits interfaces and some code from Adafruit GFX. So the Serial Wombat 18AB VGA driver will be able to use all of the Adafruit GFX interfaces. And you can see that, we're using fill screen, draw bitmap, set cursor, set text size, and then the print interfaces that everybody knows and loves for driving their TFTs or OLED displays or whatever. So if we take a look into that, this is going to be eventually a separate downloadable Arduino file, a separate downloadable Arduino library. And that's because I don't want the core Serial Wombat library to have any dependencies on Adafruit. So basically the Serial Wombat 18AB VGA library depends on the Serial Wombat library, which includes the VGA pin mode, and it relies on the Adafruit GFX that it inherits its interfaces from. So I'm pretty happy about that. I think that that's an advantage over some of the other VGA drivers out there, is that it uses all the same interfaces as some of the other things. So the Arduino serial monitor main is basically just a project that relies on all of the rest of these projects, and that's where we run our main. You can see I've got some includes here where I can actually pull in some of my example sketches, and if we go into main and call setup and then call loop, I can simulate in that manner. So let me know if there's some interest in being able to run your Arduino code within Visual Studio on the PC using Microsoft's Visual C++. And then, of course, Adafruit GFX, this is their library. I made some changes to make it compile on the PC, but it's virtually the same thing. And you can see from the result over here that we get really good results. Eventually, there will be a driver at the pin mode level that allows you to assign a color to each line. It'll be 120 color array. Each color will have a range from 0 to 7, depending on whether you want the R, the G, or the B to do that. And at the beginning of each line, then I connect or disconnect the R, G, and Bs to the SPI. So the SPI is the only device I have on the Serial Wombat chip that's capable of driving bits out at anywhere near the rate that I need them in order to drive the VGA. And so I'm pretty, is it as good as a Raspberry Pi? Of course not. But is it pretty cool for, a little 16-bit microcontroller? Well, I'm also building the architecture up to do a lot of different other things. Yeah, I really like it. So now, real quick, let's just take a look at the firmware for those of you who are interested in how I managed to achieve this on the Microchip PIC 24FJ256GA702. Here we're taking a look at the MPLAB IDE project that is all of the Serial Wombat chip stuff. We have our VGA pin mode file here, and it has the standard interfaces that allow us to talk to it through the communication interfaces and set things and all of that. So the primary resources that this uses is the SPI driver, the SPI hardware, which is configurable through the peripheral pin select. And the neat thing about that is that I can route it to any pin that I want, or I can route the output to multiple pins, which is how I'm going to drive the line-by-line color, is I can either connect the R, G, and B pins to ground, or I can connect any combination of them to the output of the SPI. In order to do VGA graphics, we need a V-sync that goes off 60 times per second, and then we need a line sync that fires a pulse on every single line, of which I believe there are 800. No, there are, I want to say 525. Is that right? So the image, the signal that we sent is actually driven by 525 lines. Some of those are the sync pulse. Some of those are the front porch, the back porch, and you could read more about VGA signaling. But essentially, we have an output compare register that generates a pulse for VSync, an output compare register that fires a pulse for the horizontal sync, and each of those have interrupts that go off. And so when they do, the VSync that indicates the top of a frame resets a line counter and resets a buffer that points into our bit frame buffer. This code is preliminary, and so some of it needs cleanup and some of it has some debug stuff in here. So, but you can see that when the the vertical sync line goes off, we set the VGA next line to 0. And then the other major one that we have is the H-sync pulse, which goes off at the beginning of each line, and it generates a little pulse. When it does that, we also get an interrupt, and so there's a period of dead time at the beginning where we don't want to pulse anything out. And so I'm using the DMA to drive the frame buffer into the SPI. Every few lines, we update the DMA to point to something new. And I'll talk about why every few lines in a minute. But one of the things that's nice is to help even things out without setting up the DMA yet. I can shove some blank pixels directly into the SPI buffer, and that kind of gets it moving immediately. You can also see that I've got a little bit of a delay in here where the interrupt fires, and then we wait a little while and just busy wait. This interrupt is the highest interrupt in the system, and so this eats up a little bit of CPU time. But what this does is it helps balance out any situation where I get a lower interrupt that fires and I'm still in the context switch before I can do a higher interrupt pulse. And that tends to clean up some of the horizontal jitter that we saw earlier. So we drive out, we set 32 bits worth of data in there. And then after we do that, we look at what the color for the next line to go out is. And using the peripheral pin selects, we either set the R, the G, and the B lines to hook up to the SPI or to the port register, which is set low. At that point, then, we've got bits that are coming out, which are the ones that we loaded up into the SPI earlier, but we want to be able to fill in the rest with the frame data. So we enable, I'm using DMA channel 5, and we set that up. We had previously pointed that at the SPI. After we get into this interrupt for the horizontal line, then we enable that DMA channel. And so it will feed it the remainder. It takes we're 160 bits wide. And so it takes 20 bytes of data. And then there's a 21st byte, which is 0, which assures that the last thing that comes out of the DMA is low, which then it shuts off color for the remainder. When the DMA completes, it fires this interrupt, which then we have the VGA DMA, and I've got some cleanup to do here to go back and generalize this for pins that aren't in DMA mode. But it comes in here, and basically it's just looking at the various lines. So one of the challenges that we have is that the fastest I can clock data out is at 8 megahertz, and that's not fast enough to be able to drive 640 separate bits in the amount of time that I have to put together the horizontal line. And so what I've done is I've said, okay, we're essentially going to combine 4 VGA pixels into one Serial Wombat VGA driver pixel. So the pixels are essentially 4 wide, and they are 3 lines deep. And so you say, well, shouldn't they be 4 lines deep to make it a square? Well, the answer to that actually is no, because at the 8 megahertz clocking that I have for the SPI, the pixels are actually a little bit shorter than what they should be. And so in order to make them look square on the VGA display, we duplicate each line 3 times, because the pixel is 3 times as wide as a normal pixel, so we make it 3 times as deep as well. And what you can see over here on the display is the net result of that is that we have a black box that the Serial Wombat is set at graphics 00 and goes almost to the end. So we have some black framing around here. I can't get rid of that. That's the best I can do with this particular system. If I was writing this whole thing in assembly language, I could probably do some better stuff if I said, okay, this is the only thing the Serial Wombat chip is going to do. But the nature of the chip, to the degree possible, I try to make it so that the users can intermix any combination of pin modes that they want. That said, you will run into some CPU limitations. You could not run this VGA driver and then also say run a bunch of pins that are doing software-based UART or something like that. So, but generally speaking, for something that I think is mostly a frivolous, fun feature, I'm really, really pleased with it. So the VGA interrupt basically comes in here, and it looks at it. You can see every 3 lines we generate a new address to point the DMA to, and we generate whatever the next color is supposed to be to come out of that. I won't go into how all of this works, but the important thing to know is that there's an output or a CCP that drives the that drives the VSync, and that's where we reset our line number. There's a much more frequent one that fires at the beginning of each horizontal line. At the beginning of each horizontal line, we feed the SPI with some blank data, then attach it to the DMA. At the end of the DMA, that's where we do our calculation for what needs to happen at the beginning of the next line. And that just repeats over and over and over again. And, I let this run last night, came back this morning, at which point it's pushed out billions and billions of pixels, and, pretty happy with that. So, let me know if you have any comments. I think probably there won't be a lot of change requests that I can implement because I'm going to conform to the Adafruit GFX interface, and I feel like I've really squeezed every last drop of performance out. So, questions like, oh, could you make every pixel a different color? No, I don't have the ability to clock out R, G, and B in parallel in a way that would make that happen. Can you implement more than 7 colors? No, because each line is either attached to the RGB line or it doesn't. So, there's some serious limitations, but the microchip PIC 24FJ256GA702 really was never intended to be a VGA driving chip in software. So, on balance, I'm pretty happy with it. So any comments you have down below, would be interested to hear them. Let me know what you're doing with your Serial Wombat chips. And if you've got some project that you've been doing with the Serial Wombat chips, send me a video link or a set of pictures that I can use in my next video. And if you're within the US, I'll send you some interesting prototype materials, some stuff that's not available to the general public that I've been working on that you may find interesting. So that's all I have for now. Everybody have fun. Keep making stuff.